Hello everyone, this is the lecture for section 4.6, exponential and logarithmic equations. At this point, we've covered everything that we need separately for exponential functions and logarithmic functions, right? And we know how to go from one to the other and from the other to the other, right? So we know, in particular, we know how to get to, if we have an exponential version, we can get to a logarithmic version, and vice versa, right? Okay. We are now going to get into the part where we use all of that we learned, right, from section 4.1 to 4.5 to start solving equations, okay? As I mentioned a couple weeks ago, right, exponential functions are the things that turn up if it's not linear, if it's not polynomial, right? The next thing up is exponential and logarithmic equations that show up, okay? So we need to figure out how to solve stuff with it eventually, right? So that's what we're going to do this in this section, okay? So for the first thing, right, let's just go ahead and I'm going to give you guys some simple ones, right? So let's take a look at the equations that are right here. So let me do the first one first, this one, okay? At the very start, right, you guys can see that in this one, the powers, sorry, not the power, the bases are the same, correct? Okay, there's a dog barking, you guys. All right, hopefully that kills it a little bit. Okay, for this first one, the bases of the exponential function are the same, right? And we want them to be equal to each other. There's no possible way that this can happen unless the exponents are equal. So we get to do this, x minus 1, 2x minus 4. So if the bases are the same and the whole things, right, are the same, then that means the exponents have got to be the same, right? Now it turns into just a basic algebra 1 problem, right? So then I'm going to do minus 2x here. So this is going to be minus x minus 1 is equal to minus 4 plus 1 plus 1 minus x is equal to minus 3. So x has got to be equal to 3. We are done. Bam. Okay. Okay. Sometimes, as you can see in the next one, in B, for example, 1, right? The bases are the same, except not really. Right? You guys see that? Okay. So what we have to do is sort of modify. This is where we're going to use our exponential rules, right? The laws of exponents, to rewrite and hopefully get the bases the same, right? So here's what I'm talking about. 4x minus 7 is equal to 3 2x all over 3 to the 1. I can give the power of 1 to anything I want like that, right? If it's 3, you can assume that there's going to be a 3 to the 1 there, right? Now, that right-hand side now becomes this, right? Since the bases are the same, right? And we are dividing two things with exponents, this is going to be the same thing as 3 2x minus 1. Okay, so now we've just simplified this to 3 to the 4x minus 7 is equal to 3 to the 2x minus 1. Now we can use the thing that we used for a. So 4x minus 7 has to equal 2x minus 1. Oops, 2x minus 1 that way, right? So then minus 2x plus 7 plus 7. So this is going to be 2x is equal to 6. X is equal to 3 again. Bam, we are done. Okay? Okay. Sometimes the bases aren't exactly the same, right? So we got to sort of semi-force it, okay? And you can do this with anything, so long as you can make them the same somehow, okay? Hopefully that makes sense. So, for example, let me take A for example 2, okay? 256, I'm going to do this over here. 256 is the same thing as 4 to the fourth. So I can do 4 to the fourth is equal to 4 to the x minus 5. Now this becomes an algebra problem again, just like example 1. So 4 is equal to x minus 5 plus 5 plus 5. X is equal to 9. We are done. Okay? Okay. For B, it doesn't look like it. Hopefully you guys are seeing what's going to happen though. Okay? We can get it down to a common base. Okay? So I'm going to write these over here. 2 cubed is 8, and 2 to the fourth is 16. Right? So now we can do substitutions here. So 8 is now 2 cubed, and I haven't done anything with the exponent yet, so it's going to be x plus 2 is equal to 2 to the fourth x plus 1. Okay? So then what I get here, right, 2 to the 3x plus 6 is equal to 2 to the 4x plus 4. Okay? Hopefully you guys see that. Now we have everything that we had from example 1. So now it becomes an algebra problem, right? 3x plus 6 is equal to 4x plus 4, right? Minus 4x minus 4x. So this is going to be minus x. I'm going to do a minus 6 already. Minus 6 minus x is equal to minus 2. X is equal to 2. We are done. Okay? So for now, for the beginning now, right, at least for now, we are looking at just changing one of the bases into the other, or if the bases are the same, just using our exponent rules to sort of simplify everything down, right? Okay, what comes up next? Some quick checks. I'm going to try have you guys try these in class, okay? Okay, a small little warning, okay? This right here. Solve this out, right? I call it a warning for a reason, right? Hopefully you guys get it. No, can't happen, right? At all. Nope, 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 nope. Okay. So now, the way that I'm gonna explain this is like this, right? Hopefully you guys remember what something like this looks like, correct? So this is a 2 to the x plus 1. That plus 1, well, let me first start with the graph of 2 to the x, right? 2 to the x should do something like this. Whoosh, right? That plus 1 is telling me to grab my blue exponential graph, right, and move it to the left by 1, right? All right, cool. So that's based off of our ideas for transformations, what the plus and minus h and the plus and minus k do, correct? Okay, but now, look at what we want to make it equal to. We want to make it equal to -2, right? The -1 that we got from over here only moved our graph left or right. It didn't move it up or down, right? So that asymptote of x equals 0, or sorry, y equals 0, that asymptote that's way down here, has not moved, right? So in other words, we are trying to find when a function, 2 to the x plus 1, will be negative, and it never goes negative at all, right? Right? This right here, we want it equal to, let me explain a little more, right? We want this graph, we want this blue graph, right, to be equal to -2, -1, -2, right? Can't happen. Okay, so I'm gonna show you guys something's gonna happen later in one of the quick checks, right? That I'll show you guys. I'll explain it a little more, right? Where once you get something like this, right, you can just go ahead and say like, I'm done. This can't happen. No possible solutions. Okay. All right, cool. All right, so now we're getting into the good stuff. This is the stuff that you're going to more likely see when you go into chemistry, when you go into physics, when you go into higher end math stuff, right? Okay. Solving things, none of these, right, um, have the bases the same, right? In one case, I'm going to do that one last. There is no similar base, okay? So how do you solve it, right? So let me go ahead and start with this one first, with B, okay? So the rules that you remember back from algebra 1, right? They still work here, right? So the idea to solve part B, I want this by itself somehow, okay? So I there's a multiplication in between, so I'm going to grab that multiplication and I'm going to eliminate it. I'm going to be dividing by the 625, okay? 625 divided by 625, okay? Uh, 5 to the 3x plus 3 is equal to 125 divided by 625. If you reduce this, this is equal to 1/5, okay? And that 1/5 is also, you can also write it, right, as this, 5 to the negative 1, okay? So from here, we can do this. 5 3x plus 3 is equal to plus 3. Whoa, went too far there. Plus 3 is equal to 5 to the negative 1. Now it becomes an algebra problem, right? Okay. 3x plus 3 is equal to negative 1, right? Minus 3 minus 3. Whoops. 3x is equal to negative 4. X is equal to negative 4 over 3. We are done. Okay? Now, this is the most simplest way to do it. Okay? But I want to show you guys something a little bit more complicated. Well, not complicated, but something that, for the most part, is going to be the operations that you're going to be using from here on out. Okay? And I'm going to start with this portion right here. Okay? Okay. So I'm going to actually scroll up a little bit, and what I'm going to do is I'm going to write this down. A to the B is equal to C, and it's basically our boomstick. You guys remember, right? Okay. Log base A of C is equal to B. So if you remember this portion, this thing, right, from a couple sections ago, right, this is what I'm going to use now, okay? So notice that right here, where I left off right here, I have the left-hand side of my boomstick. I have this, okay? I am going to convert it to the equivalent exponential version, or sorry, the equivalent logarithmic version, okay? So I can rewrite this as this. Log base 5 of 125, whoops, 125 over 625 is equal to 3x plus 3. Okay, so if you follow along, right, I grabbed my left-hand side of my exponential equation and turned it into the equivalent logarithmic version. Okay, from here, you do the exact same thing. So log base 5, I have a plus 3. I want x by itself still, right? So minus 3. 125 over 625 minus 3 is equal to 3x. So then I'm going to divide by 3, divide all of this by 3. My x is also equal to log base 5 of 125 divided by 625 minus 3, all divided by 3. Okay? There we are. It just so happens, right, that both of these answers are exactly the same. They are equal. So the x that's on the right-hand side is a fancy, it's a very fancy method of writing -4/3. Try it out. Stick it in a Desmo, stick it in your favorite calculator. That's what you're going to get. Okay? Now, this is going to parlay pretty nicely into when we have to do something like this. So in this case, you guys see how 100, right, is on the left-hand side. It doesn't look like we're going to be able to finagle 100 to a base anything, right? Much less maybe 10, right? But we're not going to get any power E out of it somehow, right? So how do we solve that, right? That is where we use this thing sort of exclusively, okay? And the idea is we want to get that exponent, the e to the 2t, we want to get that by itself, okay? So this is how we do it. There's still a multiplication in between here, between the 20 and the e to the 2t, right? So I'm going to go ahead and divide by 20. Divide by 20. 100 divided by 20 is 5, so we get left with 5 equal e to the 2t. This is where we use our boomstick. This is where we use this, okay? Notice how we have the left-hand side, we can turn it into the equivalent right-hand side, right? So I'm going to go ahead and write it just by using log, right? So then this is basically saying log base e, right, of 5 is equal to 2t. If you need to write this, right, there's no shame in doing it, okay? What you'll regularly have to do, though, and this is going to happen after you get used to it, you do a couple of examples, right? Log base e, that is ln. Okay? And now we have, basically, we have it done, right? 2 times t, we want t by itself, right? So we're going to divide away the 2, divided by 2, divided by 2. So then t is equal to ln of 5 divided by 2, whatever the heck that is. Bam, we are done. Okay? And actually, let me compute that out. Got a computer, got a calculator. 0.8047 and change. Okay? Okay, so our next couple of examples are for you guys to try. Okay? Like I said, this is the thing that we're going to be doing on a regular basis, right? In our science classes. So start getting good at it. Okay? All right, so the same thing can be said. So the examples that I've been giving you guys in the past, like just are directly previous examples, right? We were given an exponential and we had to turn it into our logarithm, right? Same thing can happen in reverse, right? The same stuff can be done in reverse, okay? So let's start with just, let's say you had 2 logarithms. Thankfully, the logarithms are the same all across, right? So what can we do there? Okay, if you remember your logarithm rules, right? All of this, I can combine a bunch of this. So if I grab this stuff on the left-hand side, right? This is equivalent to log, let me actually write it down lower a little bit, log of 3x minus 2 all over 2, this is my logarithm rule, right, is equal to log x plus 4, right? Okay, here we go. If the logarithms have to, if everything has to be equal, right, and the bases are equal, in this case they're all base 10, right, then just like we had in exponents, right, the stuff inside the logarithms have to be equal. So this means 3x minus 2 over 2 has to be equal to x plus 4. Now it becomes an algebra problem, right? And if you guys remember, I can grab all of this and make it over 1, so I can do the cross multiply. So this times this has got to be equal to this times this. 2 x plus 4 is equal to 3x minus 2 times 1. 2x plus 8 is equal to 3x minus 2 minus 3x minus 3x minus 8 minus 8. So this is going to be minus x is equal to minus 10. X is equal to 10. And we are done. Bam. Okay? Awesome. Okay. Next up, suppose we have no equal logs on both sides. In this case, there's only a log on one side. So what do? Right? This is where we use, I'm going to scroll up a little bit because I'm going to rewrite it. A to the B is equal to C. I'm going to rewrite our boomstick up here, right? Log base A of C is equal to B. We get to use this thing again. So in this case, I have the right-hand side of my boomstick, right? I can turn it into my left-hand side, right? So this is equivalent to saying, right, 2 squared is equal to x squared minus x minus 2. So I grabbed my right-hand side and turned it into the equivalent left-hand side. I grabbed my logarithmic version and turned it to the equivalent exponential version. Now it's to the races, right? So 2 squared is 4, x squared minus x minus 2, minus 4 minus 4. I get this, x squared minus x minus 6 is equal to 0. So if you guys remember from back in the day, this is a diamond method thing, right? I can only make an x, there we go. I believe I did times up top, plus at the bottom, so times minus 6 minus 1. Two numbers that multiply to negative 6, but then add to negative 1, right? Negative 3 and positive 2. So and that means this is equivalent to x minus 3, x plus 2 is equal to 0. Back to first week of school, right? X minus 3 is equal to 0. X plus 2 is equal to 0. Okay? X equal 3. X equal minus 2. Bam. Okay? Now, there's a problem though. Okay? Just because we have two answers doesn't mean that both of these answers are going to work. We need to figure out which one does work. Okay? So, I'm going to go ahead and plug both of these in. So, if I do, I'm going to plug it into this thing in particular, to the inside of the logarithm. And hopefully you'll see, I'm not going to say it yet, what the problem is, right? But hopefully you guys see what's going to happen. So if I plug in positive 3, right, that's going to be 3 squared minus 3 minus 2, right? 9 minus 3 minus 2, that is going to be 9, 4. Okay? Now, let me plug in negative 2 now, right? Minus 2 squared minus a minus 2 minus 2. At least I think this is going to have a problem. Oh, not yet. So this is going to be 4 plus 2 minus 2. Okay. 4. Never mind. I take it back. Both of these are answers. So the problem is this. And I think I got ahead of myself. It's going to happen in the quick checks. One of the quick checks will not work. And I hope one of you guys see why. Okay. Both of these answers, right, if you plug it back into the logarithm, may produce a negative number. Right now, you guys do remember there's one more thing we have to add that we can't do in math, right? We can't take the logarithm of a negative number. So we have to double check that. We have to double check that the answers that get produced are actually possible in a logarithm. Okay, so that's why I had to do this. Thankfully, though, both worked. So we're good. We're all right. Okay, what comes up next? Quick checks. We're getting into the good stuff. This is solving out logarithmic equations, right? Okay, so now we're getting into parts of the class that are much more applied math than sort of theoretical math. Okay, so in this case, right, we have a population of a small town, and it is modeled by this equation right here. Boom. Okay, and t is measured in years since 1990. Okay. Okay. The question is asking, in approximately how many years will the population reach 20,000? Okay. Now, notice what I'm asking you to do here, right? Well, I am asking you to grab the population equation, right? T, whoops, is equal to 1650 e to the 0.5t. And I'm asking you, when will this be equal to 20,000? Right? In the past, I gave you a t value. I gave you a t value and you gave me a time. Right? Oh, sorry, the other way around. I gave you a t value, I gave you a time, and the equation gave you the population, correct? Whatever was solved. In this case, right, I am asking for a time for when the population is, I'm asking you for the time for when the population is 20,000, right? This is where we're going to use, this is what's going to be happening on a regular basis in your science classes, okay? That you have to solve for a time. You have to solve for an amount, right? Okay? So we need to solve that thing that's highlighted in yellow, okay? Like I said before, the same rules that you had before, right, apply here. So then there's a multiplication between here, right? I need the e to the 0.5t by itself. So I'm going to divide away the 1650. Okay? The zeros cancel. Okay? So I get left with this. E to the 0.5t is equal to 2,000 divided by 165. Whoa. 165. Okay. Okay. So I actually need to scroll up a little bit. A to the B. You guys see why I call it the boomstick? Log base A of C is equal to B. Okay. I'm going to use, if you guys notice, right, I have the exponential version. I'm going to change it to my logarithmic version. So I'm going to go to this side of the equation this time. I'm going to try to get this thing, right? Okay, let me highlight it so you guys can see it. Boom. Okay, here we go. So then I should be able to grab this, right? You take a look at it. It's going to be log base E, right, of 2,000 over 165. That is going to be equal to 0.5t. Okay, I still want t by itself, right? So divide by 0.5, divide by 0.5. Okay, my answer, my final answer, t is going to be equal to ln 2,000 over 165 divided by 0.5. We are done. Okay, now this is where you would want to get some decimal value here, right? And if you plug this into the calculator, you're going to get 4.989. Okay, so according to my calculations, right, the population ooh, population will reach 20,000 in about 1995. Okay, 4.989 is pretty close, pretty darn close to 5 years, right? Uh, the measurement starts at 1990 plus another 5 years. That's 1995. We are all done. Okay, but notice what we did now, right? We are grabbing exponential. We are now grabbing exponential models, right? That usually require a time, right? We usually give it a time, and it gives us an amount, right? We are now asking for an amount, and it's going to give us a time. Does that make sense? We are solving out for stuff that's in an exponent. That's what this stuff is useful for. Okay. Thing that comes up next is quick checks. There's only two. I'm pretty sure you guys are going to have enough of a hard time with both of these. Okay. And after that, it's lecture questions. Once we get once you guys have enough practice with the quick checks, right, you guys are going to see these lecture questions as super simple. The numbers that are going to pop up, right, they will look complicated, but the overall concept is very, very simple. I'm not going to make you guys do anything harder than the stuff that I gave you up above. Okay. Besides that, that is it. If there's any questions on the stuff that I just covered here, ask me during our quick check times or ask me during my office hours. Okay. Besides that, happy studying.